Thank you, and thanks to the organizers for this event. It's really fun. Unfortunately, I haven't been able to attend much because I just got back from a conference where I got sick. I was just talking about it a little bit, so hopefully you can understand me okay. If not, feel free to ask questions. Um, so uh, I'm just going to get started right away with what a shepherd group is because I think it's likely people haven't ever heard of this before. So it starts off if you've seen an Artin group or Coxeter group, the definition starts off very similarly with simplicial graphs. So that just means no loops, no double edges. We assume the vertex set is finite. Um, and for each edge, we put some number that's at least 3, and we could put infinity if we want. Um, if there's no edge, then we'll still define this Mij to be 2. And if we're drawing the diagram, sometimes we'll just leave off a 3, so there's less clutter in the diagram. So what differs now is that we'll put labels on the vertices as well. And I'll call those PI, and we'll label those anything 2 or bigger, also possibly infinity. And one stipulation is that if an edge label is odd, then the 2 vertex labels on the sides need to be the same. And I'll explain why that is in a minute. So this diagram defines, it gives you the data to define a group, which we call the shepherd group. So the generators are going to be the vertices. The relations are just if you take a vertex and the label is not infinity, then you say that vertex has order pi. And the only other relations are if between 2 edges, the vertices satisfy this kind of braid type relation, where you have this alternating word in I and j, starting in I of length Mij is equal to this alternating word, but starting with j, but with the same length. And that's whenever it's less than infinity as well. So in particular, if this is 2, then it's just a commutation relation. It says Ij equals Ji. So some special cases, if all the vertex labels are 2, then this is a Coxeter group, just the definition of a Coxeter group. And if all of them are infinity, then it's the definition of an Artin group. I'm not going to get too into details into what these are, because it's not super relevant. But if you've seen Artin groups and Coxeter groups, likely Coxeter groups in GGT, you've probably seen, then it should give you some sort of intuition for the definition here. So just so they're not, just completely, generally abstract kind of useless things, what are some reasons you might care or might think to look at things like this? Well, I mentioned Artin groups. If it's all infinity, it's an Artin group. Well, if you put vertex powers here, then it's sort of like quotienting out the Artin group by powers of its generators. So you can sort of think of this as, very broadly, not any kind of specific way, that it's kind of similar to quotienting a mapping class group by powers of its Dane twists, because the Dane twists will finitely generate the mapping class group. So this is, not too dissimilar to what's going on there. And in mapping class groups, this has kind of given some interesting results. For example, Francois Damani, Mark Hagan, Alex Sisto in 2018 showed that when you take large enough powers, the group is acylindrically hyperbolic. And then just recently, Baerstock, Hagan, Martin, and Sisto showed that some of these are also HHGs. So, kind of some good motivation that maybe there's something to look at here. Another source of motivation comes from the complex reflection groups. So not all of the shepherd groups are complex reflection groups. Like you might be familiar with the fact that Coxeter groups come from real reflection groups. But that's not true in general for Shephard groups. What we can say is that the finite Shephard groups come from certain complex reflection groups. Namely, they're the symmetry groups of so-called regular complex polytopes, which let's see, I have a picture here. So they were first identified by Shephard in 1952, hence their name. And Coxeter has a wonderful treatment of them, similar to his work on the real regular polytopes. So here's some figures. I probably, won't go into too much detail, but these things that look like triangles are really sort of projections of complex planes, or complex lines, I should say, and they intersect at these vertices. So, for example, a complex polygon is made up of points and complex lines, which are two-dimensional. So they're very interesting shapes, but I won't discuss them too much. So before we can really discuss about um, what we can prove, let's look at like some very, very straightforward results. So if we think about going back to Artin groups, I keep mentioning, um, we know very little about Artin groups in general. We know a lot about Coxeter groups. Artin groups, we know very little. There are a couple of facts that we know for every Artin group. For example, if we take a subdiagram, so you take a full subgraph, which means, if you have two vertices that were adjacent in gamma, then they're still adjacent in lambda. Then it will make a Shephard group, or Artin group or Coxeter group, and you can look at the subgroup generated by the same vertices, and there's a natural surjection. If you just look at this subgraph by itself generates some Shephard group, and then it lives inside another Shephard group. In general, we don't know if those two things are isomorphic. But if it's an Artin group or a Coxeter group, then we always know that it is. So this is one of like the very few facts we can say for all Artin groups. And we can't, so far can't really say it for all Shephard groups. So it's kind of telling us, this is a very, very broad definition. So we should have some conditions that make it a little more tractable, and give us something to sort of work with to be able to prove much of anything. So I'm going to introduce just a bunch of these conditions now. I'll go through them a little bit slowly, so because they're kind of the key to the proofs or the results. So first is the two-dimensional condition. So this says that if sorry, I explained the notation here, because I forgot. If it's W sub lambda means it's the Coxeter group. So ignore all of the labels that were on this diagram and replace them with 2 to get a Coxeter group. Oh, I'm sorry. So we say that it's two-dimensional if every Coxeter group that's generated from this graph, and it's finite, it means that it has to have 2 or fewer vertices in the graph. So for example, if you take the braid group, I'm sorry, I didn't write it out. The braid group's diagram is just a straight line, and it's not two-dimensional because the braid group's Coxeter group is the symmetric group, which is finite, regardless of how long this like string is. But if you take, say, a triangle and all of the edge labels are, say, 7 or something, then that would be two-dimensional because every pair generates a finite Coxeter group, but the whole thing will be infinite. It'll be some reflection group in H2. The FC condition originally stood for flag complex. That's not really that important. But it says if your diagram has no edges, if your subdiagram has no edges labeled infinity, then it has to generate a finite Coxeter group. This is not true in general. For example, if you take an affine Coxeter group, so if you take a triangle with all of the edges labeled 3, then that will be an infinite Coxeter group. It will be like the Euclidean tiling. It'll be the reflection symmetries of the Euclidean tiling, the tiling of Euclidean space by equilateral triangles. Sorry. Um, so there are no edges labeled infinity in there, but the group isn't finite. It's this infinite reflection group. So that's an example of something that's not type FC. Something that is type FC, of course, is something like a finite Coxeter group to begin with, or excuse me, if you take, say, like the braid diagram, and at the end you put an edge labeled infinity, that something like that would be type FC. And then this condition is the first two are kind of common in Coxeter and Artin groups. This one is sort of unique to Shephard groups, which I call FPA to stand for the finite parabolics agree. And this basically just says that if the Coxeter group is finite, the Shephard group has to be finite as well. I'll explain that in a second. Actually, I'm going to jump around here. So the top half of this diagram is all of the finite Coxeter diagrams. So if you take the Coxeter group corresponding to these diagrams, it gives you a finite group. And below this are the finite Shephard groups, where you can add these labels and you'll still get a finite group. So you'll see there's many fewer. So it's kind of a strict criterion to say that if you add, so the FPA is basically saying if you take a subdiagram and it gives you a finite Coxeter group, then it must have given you a finite Shephard group. So it's basically saying it has to be built out of these 5 diagrams, which is not, very flexible. For example, if I just take H3 and put like 3s on all the vertices, now that doesn't satisfy FPA because each edge group will be finite, but the whole thing will generate an infinite Shephard group, even though the Coxeter group is finite. Excuse me. So sorry. And the last one I want to just mention briefly, they're called Dyer groups, which are sort of they're related. I'm not going to focus too much on them. I just wanted to mention them for some nice results that have been proved recently. Where if you have any vertex label that's bigger than 2, all of the edges coming off of it have to be 2 or infinity. So it's sort of like a right-angled thing, but you can have some subgroups that are Coxeter groups that aren't right-angled. Okay, so with all of that out of the way, I'm gonna give a big list of the results that we know so far, and I haven't been able to find, many other results. I don't know if it's, people use different names for these or what, but it seems like they're not super well studied. So first, I want to mention Dyer groups. So back in 2022, Luis Paris and Mireille Sorgel showed they have a really nice solution to the word problem that kind of mimics the solution to the word problem for Coxeter groups. And then in another paper, Mireille shows that they're cat 0. So one of the only other results I could find is if you combine all 3 of those other conditions I have, so the finite parabolics agree, the diagram is type FC, and it's 2-dimensional, then the group is biautomatic. This is in, I believe, Weiss's thesis in 09. And then last year I had a paper where I show that if the finite parabolics agree and it's type FC, then it's co-compactly cubulated. In particular, by this work of Niblo and Reeves, it implies it's biautomatic. Excuse me. Um, and if it's FPA, with this annoying technical thing, then it's the group is cat zero. So this just means you can't have any of this diagram in it. And the only reason why is because we don't know how to show some piecewise spherical complex is cat one for this thing. So it's not saying it's like a poison subgroup. It's just saying I don't know how to do it. Okay. So upcoming, which I'm very excited about. So I'll remove the FPA and kind of just look at what happens from like a more pure Shepherd group perspective. So now we're not really basing it on these Coxeter diagrams. We can kind of just look at it for what it is. So if it's two-dimensional, you can show it's acylindrically hyperbolic when the diagram is large enough. This is based on work of Nicola Vascow in 21. And you can show that they're weakly relatively hyperbolic when the Coxeter group is hyperbolic, which is also identical to a result for Artin groups by Charney and Crisp in 2005. Um, the really interesting thing is that if it's two-dimensional and it doesn't satisfy FPA, then it's actually not cat zero. And by that, I mean it cannot admit a proper action on any cat zero space. So that I will explain a bit more because that might be one of the more interesting parts of all of this. So here are some example diagrams of groups that satisfy FPA. So they're like you can have like an affine type Coxeter group where you add some vertex labels. You can have these triangle groups. And notice here, P has to be 2, 3, 4, 5, so the edge group stays finite. Now, if P is bigger than 6, is 6 or bigger, so I didn't put too many on this page because I'll explain in a second. If you take P bigger than 6, now these edge groups are going to be infinite, and so it won't satisfy FPA anymore, and now all of a sudden this group is not cat zero. Even though here, when you take small powers, you get a cat zero group. Strangely enough, if you take larger powers, it's not going to be cat zero anymore. Um, and the reason for this, so the reason I didn't put that many diagrams is because just for dumb technical reasons, I used Dinkin diagrams instead of presentation graphs, and it's hard to draw two-dimensional things with Dinkin diagrams. So there are a lot of examples, and unfortunately, I didn't really have the space to like draw out a bunch of 2D diagrams. Another very interesting one, though, is if you take just a single edge and label it 6, 3, 6, if it's labeled 3, it's going to be a quotient of the 3-strand braid group. And if you take quotients by powers of 6 or more, now all of a sudden it's not cat zero. So we know the 3-strand braid group is cat zero. This is kind of a long-standing result. It's conjectured that all braid groups are cat zero. In fact, it's conjectured all Artin groups are cat zero. But there's this very explicit quotient by powers of the generators where it is not cat zero. Okay, so how are we able to show any of this? The central object is this sort of an adaptation of the Davis complex and Lean complex for a general Shephard group. So if you're familiar with either of these, the definition for Shephard group, the kind of naive definition actually is basically exactly the thing you want. You get a nice co-compact action with a nice fundamental domain. If the finite parabolics agree, then this action will be proper. So it gives you a nice model for the geometry of the Shephard group itself. And the other nice thing about it being FPA is all of these finite subgroups that stabilize it are complex reflection groups. So now we get to use this really nice geometry of the complex reflection groups, sort of like you can use the real reflection group geometry when you're talking about the Davis complex of a Coxeter group, since all of those finite stabilizers are also, real reflection groups. So this allows us to show that those two results about being co-compactly cubulated and being cat zero really use heavily this complex reflection group structure. So the second half of this, so the reason we're able to show it acylindrical hyperbolicity and weak relative hyperbolicity is because even though the action isn't proper, the Deligne complex is still cat zero, and it acts very nicely on the Deligne complex. And we're able to show it's cat zero in basically identically the same way as you show like in Artin groups is cat zero. And so this action, the fact that it is so similar to the Artin group makes us able to basically almost word for word adapt the proofs for Artin groups being acylindrically and relatively hyperbolic to the Shephard groups. Okay, so why are some of these not cat zero? So if we just restrict ourselves to dihedral Shephard groups, so just two generators with one edge, and then I'll let H be this quantity, which is 1 over P plus 1 over Q plus 2 over M. This is sort of like the key quantity, I guess. The main kind of observation is that a dihedral Shephard group is a central extension of a rotation triangle group. And this coefficient sort of controls where that triangle group naturally lives. If it's bigger than 1, then it's over S2. If it's equal to 1, it's the Euclidean plane, and less than 1 is the hyperbolic plane. So in particular, if it's less than 1, then the group is actually a central extension by Z, and this Euler class has infinite order. So you go through like these fun cohomology arguments, and all of this implies it can't virtually split over its center, which is something that all cat zero groups do. So it can't admit any proper action on a cat zero space. Excuse me. So this is, all kind of abstract nonsense just depending on your opinion of cohomology. So I'll give some like explicit corollaries as to get a handle on what this means. So if you take H equal to 1, then what this kind of means is the Shephard group's actually commensurable to the three-dimensional integer Heisenberg group, which is, one of the kind of more interesting, like simplest nilpotent groups that we study in geometric group theory. So being commensurable tells you a lot. Like, for example, it gives you virtual nilpotency, and it tells you that the group is not semi-hyperbolic, just for like Dane function concerns. And if H is strictly less than 1, then it's commensurable to what's sometimes called the universal central extension of a hyperbolic surface group. It's not exactly the right terminology because universal is usually used for something else that I don't care to get into. But some consequence is that it's biautomatic because it's a Z central extension of a hyperbolic group. And Neumann and Reed says those are biautomatic. So if H is less than 1, this dihedral Shephard group is biautomatic, which is nice, but doesn't really propagate to like higher rank Shephard groups, unfortunately. And so this isn't exactly a consequence of what I've been saying, but you can use all of this to show that the Shephard group is a uniform lattice in the isometry group of the universal cover of SL2R. And you can actually do it very explicitly, like give the generators and say this generates a Shephard group. So I wanted to do a quick example. Maybe I don't have a ton of time, but I'll just say in words, oh, what happened there? I thought I could. Um, can people see my mouse pointer? Okay. So if you think about maybe the Cayley graph of the Heisenberg group, a lot of times maybe you're told, maybe you've seen this, maybe not. If you start maybe, oh God, red is not a good color. Maybe start here, and you trace a path, and I don't know, go around there. Then you can sort of think this, okay, this is a very vague description. I'm very sorry, but hopefully it gives some insight. Um, Doing this in the Cayley graph of the Heisenberg group is sort of like you're going up a level as you're going up as you travel along this path. And when you return to the starting point, the number of squares that you've encircled is sort of how far you are vertically from where you started. So if you think of, sorry, these red squares as laying on the plane, you travel along and you're going up and up and up. And when you get back, you're sort of that many squares above where you started. So interestingly, it's actually very similar for these shepherd groups. Um, I thought that would clear it. Okay, there we go. So if you start, say, here and just traverse the hyperbolic plane, I am including some triangles in there, blah, blah, blah. And you come back to where you started, you think of it exactly the same thing. You have H2 here, you're walking around, but as you're walking, you're sort of picking up height. And then when you get back to where you would have started walking, the vertical distance you've traveled is the number of red squares that you've collected. And yes, there are some triangles in there, but the triangles are coming from the vertices. So really the 8 comes from the edge label, which is why it's a square, because it's half of 8. I don't have much time to explain that, but just trust me. And the vertex powers sort of don't get included. They don't contribute to like this monodromy thing. But modulo those couple of details, it's very identical to a Heisenberg group where the distance, like the number of levels you go up, is how many of the red squares you collected in this closed path on just H2. Um, and yeah, sorry for the abrupt ending, but thank you for listening.
So let's thank Katherine. And does anyone have any questions?
Yeah, sorry, I wanted to ask something. So yeah, at the beginning you mentioned that like we should think of them as like the analog of quotients of mapping class group by powers of the n-twist. Like, is there any deeper analogy between these, or just like
Yeah,
take the
actually, there
or
is. There's a lot of work done on what are called geometric representations of Artin groups. So those are Artin, like taking Dane twists in a mapping class group that generate an Artin group.
yes.
So sorry. So yeah, if you just think about it like that, then it is literally just look at the subgroup of the mapping class group that generates the Artin group, and then mod it all out by the powers of the Dane
Oh,
twists.
I see.
Yeah. Now there are a lot of Artin groups that don't have these kinds of representations. So it's I think I've heard Artin groups and mapping class groups kind of described as cousins, sort of. They've got a lot of similar behaviors. I guess another thing might be to think about is the curve graph for a mapping class group. There's an analogous thing for Artin groups, and I guess an open question is its curvature properties. So I guess like this, the HHG paper here was about the curve graph, and so that's something you could ask about the Artin groups too. Is if you mod out powers of the generators, do you get some HHG structure on the curve graph?
Mhm. Okay, yeah, thank you. Because, like, for example, this is just like self-advertising, and sorry if I do that, but like with Alessandro's sister, we're working on like doing the kind of same thing for some quotients of Artin groups, in which you take some like generators and you quotient by that, and sometimes you get a like hierarchical hyperbolicity, sometimes you get something like that. So yeah, but yeah, thank you.
Yeah.
Okay, I think let's thank Katherine again.